A few weeks back, we published an AI-powered demo app and it took off. It kind of went viral on Hacker News and Twitter, and thousands of people have tried it out and gave us tons of feedback. So we wanted to record a video that showcases what the app does and how it works, as well as do a code deep dive. So in case you haven't tried it out yet, you can try it out at neon.tech/YCmatcher. And the app, essentially what it does is it allows you to submit an idea and get a list of similar companies Y Combinator has invested in before. And in case you're unfamiliar, Y Combinator, or YC, is a startup accelerator. So for example, I can do ride-sharing app and carpooling. And I'm getting results for companies that are operating in this space. So transportation services, long-distance carpooling, transports groups and businesses together, van pooling, largest vehicle sharing platform, and so on and so forth. So you might be wondering, what makes this app special? Well, it's the fact that it doesn't rely on traditional search where you do keyword-based matching. Rather, it uses semantic search, where we can understand the meaning behind a user's search query. So for example, I can say instead, an app that gets you from point A to point B and you split the fee. And you'll notice that we still get results for companies that are operating in this space. We were able to get the search query and find the most relevant results. So here, helping travel companies sell transportation online. Well, we were very vague. We said going from point A to point B. We didn't specify how. It could be by a car, airplane, whatever. So that's why we got this result. And again, pay for parking by turning your car off. Well, it was like point A to point B, travel, car, and that's why we got this search result. And again, an app that makes rideshare drivers up to 30% more money. So that's because we don't rely on keyword-based matching. We actually rely on vector embeddings and vector similarity search. A vector embedding is a vector list of floating point numbers. We can use it to represent unstructured data, like text, images, audio, or other types of information. And what's powerful about embeddings is they can capture the meaning behind the text, and we can use them to measure the relatedness of text strings. So the smaller the distance between two vectors, the more they're related to each other, and vice versa. So if the distance between two vectors is big, this means they're not related to each other. Consider the following 3 sentences summarizing different books. A young wizard attends a magical school and battles against an evil dark lord. A group of friends embarks on an adventurous journey to destroy a powerful ring and save the world. And then a detective investigates a series of mysterious murders in a small town. So what we can do is convert each text string to a corresponding vector embedding. So the first summary can have this embedding, for example, the second one, a different one, and the third one, a different one. And if we want to find out which 2 summaries are most related to each other, we can calculate the distance between every 2 embeddings. So the first one and the second one and third one, and then the first one and the third one. And the 2 embeddings closest to each other distance-wise will be the most similar. And at a high level, this is how the YC Idea Matcher app works. We first convert the user search query into an embedding, and then go through every company description and return the most similar ones. So now we need to understand 2 things. How do we generate embeddings? And 2, how do we actually do the distance calculation between vectors? One way to generate embeddings is to use OpenAI's Embeddings API. There are other embeddings APIs out there and AI models you can use. However, for our project, we used OpenAI's embeddings model. So right now I'm looking at the docs, and first they're covering what embeddings are and common use cases. So search, That's what we're doing with YC idea matcher, because we're returning the most relevant results based on the user search query. We can do clustering because, again, if we're able to determine the similarity, well, we can do grouping. And on the other hand, we can also do anomaly detection because we can detect, okay, after we create groups, there are outliers that we can then remove. And again, recommendations is similar because we can find the most relevant items based on an existing list of other items, because we'll just find the most related items. So for example, consider Netflix watch history. You watch several movies and TV shows. Well, you can do recommendations using embeddings because you'll be able to find the most relevant movies or TV shows to what the user has already watched, which is great. And to use the OpenAI's Embeddings API, all you need is an OpenAI account and an API key from OpenAI, which you can find in your account settings. And all you need to do once you have these two things is you can just send an API call to this endpoint, api.openai.com/v1/embeddings. And in the request body, you will specify the input, which is the text string here, and then which AI model to use. So to generate embeddings, we use the Ada 2 model. This is the latest one. And however, there are other ones provided by OpenAI, and pretty sure they'll keep releasing new versions as well. And once you send the request, you will get the following example response. So you'll see a data array, and inside it, we have an object called embedding, and the embedding is an array of floating point numbers. So this is how we actually get convert the text to an embedding. And now it's time to go over how you actually do vector similarity search. So how do you calculate the distance between two embeddings? And to do that, we actually only need Postgres and pgembedding or pgvector. So pgembedding or pgvector, they're both Postgres extensions. pgembedding is built and maintained by the Neon team, and you can use these two extensions to do similarity search in Postgres. So the high-level summary, what you need to do is first you enable the extension, it's called embedding, and then you define a column where in this column you'll store an array of real numbers. So the floating point numbers that we have. So here we are creating a table called documents. It has an ID column, which is the primary key, and then an embedding column, which will store like our embeddings. And then when you're inserting, you're just doing an inserting into documents, the ID and the embedding. And the first row, it has an ID of 1, and then this embedding, and then 2 has this other embedding, and so on and so forth. So now, so far, all you did is just create a table with a column for storing embeddings. And then when you're fetching data from the database, so when you're doing a select, here you're doing a select and just returning the ID from the documents table, you will order by the distance between the embedding that is in the column that's stored, that is in the row that is stored, against another embedding. And then you're doing a limit 1. So what's happening is in the documents table, you are doing a comparison between the embedding that's in the table and then the embedding that's specified in the query right here. And then for each row, you're doing this, and then you're sorting the result by the shortest distance. So order by default is ascending. So essentially what we're saying is, get me whatever is the closest or most relevant result based on this embedding. And we're doing a limit 1 because we just want the most relevant results. If we want multiple ones, we can just do limit 3, 4, 5, or whatever. In YC idea matcher, we're doing like a limit 5 because we're returning 5 companies as part of the result. So that's pretty much it. At a high level, this is kind of how everything works. We generate embeddings, and these embeddings are stored in a Postgres database. For that, we'll use Neon. And then whenever we want to do a search, well, we get the user's embedding, the user search query, convert it into an embedding, and then just return the most relevant result from the database. So now let's actually see what that looks like, in practice and how the demo was actually built. So right now I'm in the code base for the project. It's open source. I'll leave a link down below in the description. And I would say the first step was first getting the data. And to do that, we actually just grabbed the data from Y Combinator's public API. So Y Combinator, they have a Y Combinator API. I think it was api.ycombinator.com/v0.1/companies. And this API just returns an array of companies, and then it's paginated, and like each object just represents a company. So you'll see each company has an ID, a name, its slug, what is its website, the logo, the one-liner description, the long description, the team size, the URL. Like, it is very comprehensive, where it's operating, locations, and like which industry, and if there are any sort of tags. So the first step was actually just us collecting this data. And to do that, we just wrote a script that did the following. So first, the script, there's like a run script. This is using TypeScript. And we just manually ran it and left it to run. And there are two steps. So the first step is creating the company's table. And this function, what it does is, you guessed it, creates a table. So first, we're enabling the extension if it doesn't exist, pgembedding. And if you want to use pgvector, they're both compatible, and we have docs on it. I'll leave a link to the docs on how you can just migrate from pgvector to pgembedding. And to do the same, you just do the guide in reverse. And then we're just doing a create table if it doesn't exist. The table is called companies. And we're just defining several columns. So an ID, a name, a slug, a website. This is the exact same format as the data that gets returned from the API. And you have the one-liner, the long description, and I'm wrapping long description, one-liner, and team size in double quotes, because by default, Postgres will lowercase the text. And if I do it without wrapping it in double quotes, it will be like this, which is not what I want. And then we just have an embedding column, which is an array of real numbers. And that's it. This is what this function does. If there are any errors, we'll see what the error is. Now, there are companies that didn't have a long description. So I actually, after the script ran, I manually just removed these results. So we just created the companies table. And now the next step is scrape companies. And this is a function that takes a URL, and we're passing in the API URL that we just looked at. So this function, what it does is first we get the response from the API. So essentially we just do a fetch and get this result. And then we are pulling companies and next page from the responses data, because again, it's right here. So we are pulling companies and next page, these two values. And then for each company, we're extracting the long description. And then we have a function called generate embedding that takes text and then generates the embedding and returns it. So what we do then is just store the company. So this is another function that takes two arguments. Company, this is an object containing all the company data, and then the actual embedding. And the generate embedding function, what it does is it does what we kind of explained. We just do a post request to the embeddings API, pass in the text string, pass in the model, pass our OpenAI API key, get the data, then that's it. That's how we get the embedding for each text. And we're doing this for every company's long description. And then we have the store company, which stores. And so to paginate, we will check the next page. If there is a next page, we will recursively call the same function again, so scrape companies, while passing in the next page URL. So here you will see that the next page, this is the page with the parameter. So right now I'm on the first page, and the next one is this one. So that's kind of how we're looping through all the pages. And there are like in total 177 pages. So and each like page has 25 items in it. So it's like 177 times 25. It's like 4,425 companies. However, the last page, like if we do like page 177, we will find that, or like 176, we'll find that it has 3 items. So it's more like 4,000-ish companies, or 4,400 companies, something like that. And yeah, and then the store company, this function, what it does is, well, we just grab the company data from the company object that gets passed, and then we're just doing an insert into a Neon database here. So yeah, we're doing an insert into companies, we're passing in the different values, and that's it. So then it's like company, the company's name stored successfully. And if we run the script, essentially what's happening is like we just get a bunch of logs saying like company, Y Combinator stored successfully, company, whatever stored successfully. So that's the first part, which is gathering the data. And then the next part is actually just building the app itself. So the app is built using Next.js, which is a full stack React framework. So you can have both the front end and the API in the same code base. And at a high level, like I won't be going into too many details here because it's pretty like minimal, but we have the front end, we just have the form, and the form we're using like React Query to do the submissions. So this is just markup. This is like the Neon logo. You have the hero section, which is just a bunch of text, and then the form. And we have a bunch of client-side validation, and then we submit it, show any errors, and then the response, we just render it as a list like you saw in the final app. So the front end is pretty simple, and that's kind of how it works. And then for the API, which is the most interesting part, it's at /API/IDEA. I'm using the Next.js app router. So this is the latest version. And the way it works is I'd say we're doing a bunch of imports. We're then setting the fetch connection cache configuration to true. And this just speeds up queries by caching the connection string. This is specific to the Neon serverless driver, which I'm using to connect from this API endpoint. And this API endpoint is actually an edge function. So typically you can't establish a TCP connection from edge environments and serverless environments. So the Neon serverless driver enables you to do that by connecting over HTTP. And I'm just specifying the preferred region because by default, edge functions are deployed globally. However, I want it to be deployed in the same region that my Neon database is deployed in. So that's why I'm specifying here. And this is US East 1, which is Washington, I believe, or North Virginia. I don't remember. And then we are rate limiting. So we just have a rate limiter because, it's not bad to always have an extra layer of security so no one spams this API endpoint. And to do that, we're using Upstash, which is serverless Redis. And then we're establishing a connection using the serverless driver. And we're just doing a check, like a rate limit check, getting the body of the request and doing some schema validation. So we don't want to receive any sort of input. We want it to be a string, and the ID has to be at least 20 characters long and at most 140 characters. We don't want someone to, submit paragraphs of text because then it's a bit unnecessary. And if all the validation works and there aren't any errors, we just keep going. So if it doesn't work, we just send a 400. And after that, we just grab the idea from the request body and we generate an embeddings for it. So you can see embedding equals await generate embeddings. We're passing in the idea, which comes from the front end. And then the result here, we're doing a query, a similarity search query. So we're returning the ID, name, small logo URL, website, all these fields from the company's table. We're ordering by the embedding, and we're calculating essentially the distance between every company embedding and the embedding that we just converted. And then we're returning like the 5 most similar companies. And then we're returning the data as JSON. So that's pretty much it. Now, because we're working with a small data set, which is like 4,000 rows, which is not a lot, I actually don't have an index. However, if you're working with like millions of rows, it's a great idea to have an index. Otherwise, it'll just take too long. And to do that, we have, like, you can check out the documentation when it comes to how you can add an HNSW index to speed up queries and have them scale. So that's it. Hopefully you found this video useful and hopefully inspires you to build your next AI application using PG embedding and Neon and Postgres and OpenAI. And if this is your first time hearing about Neon, you can sign up for free. You get like a Postgres database. So we have like a generous free tier that you can try out. And yeah, if you have any questions, feel free to reach out to us on Twitter or our community forum. We'd love to hear from you.